Hello everyone. In this video, we're going to be discussing the hierarchy of asymptotic complexity. This is our sort of absolutely lazy way of understanding growth rates of functions. So, what this hierarchy is, it's an incomplete list of how certain things relate asymptotically. Things that appear lower on this list, down here, grow more slowly than things that appear at the top of this list. This list is necessarily incomplete because there are infinitely many functions we could include, and we obviously don't have enough page space here to include all of them. So, let's start at the bottom and work our way up. The absolute best runtime we can have, or best asymptotic complexity, is going to be theta of 1. This is used to describe the idea of a constant runtime. We're bounded above and below by some numbers. That's very convenient. That's the best we can hope for. Pretty much immediately afterwards, the next thing we'll likely see will be log of n. And as we saw with our limit theorem problems, we know that the base of the log really doesn't matter much. Immediately after that, we have log of n quantity squared. We then have log of n cubed, log of n to the fourth, and we can't include all of those because there's far too many. Eventually, we arrive at n to the 0.1. Immediately before that somewhere, we get to n to the 0.01, and before that, n to the 0.001. We keep marching up the hierarchy. We get things like radical n, which are a result of having a higher power of n. Similarly, we have theta of n, again, a higher power of n. Kind of immediately after theta of n, we have theta of n log n. Immediately after that, theta of n log of n quantity squared. Immediately after that, theta of n log of n quantity cubed, and so on. Eventually we get up to theta of n squared, then theta of n squared log n, then eventually theta of n cubed. We keep going up, and then eventually we get to exponential functions. Things like 2 to the n and 3 to the n, and these are in different asymptotic categories. The base of the exponential does matter. So theta of 2 to the n grows slower than theta of 3 to the n. And after those, eventually we get to things like theta of n factorial and theta of n to the n. This top categorization here, you could probably even include theta of n cubed. Whenever you're analyzing an algorithm and you're getting runtimes that look like n cubed, 2 to the n, 3 to the n, n factorial, you're in the bad territory. We're going to discuss later in this class what we mean by bad territory, but for now, we'll just keep in mind that really you want to be, when you're designing an algorithm, you want your algorithm to be down in this bottom part of the hierarchy. The further you are up the hierarchy, the worse your algorithm is in terms of its runtime. You want it to run quickly, so you want it to grow slowly with the size of the input. This is used very commonly to simplify expressions because we know what the most important term is. The things that are higher on this hierarchy are the more important terms that will appear. The lower order terms, the things that are lower on the hierarchy, are less important to our runtime.